Spectroscopy 3, mass spectroscopy. Essential idea. Analytical techniques can be used to determine the structure of a compound, analyze the composition of a substance, or determine the purity of a compound. Spectroscopic techniques are used in the structural identification of organic and inorganic compounds. Improvements in instrumentation. Nature of science. The mass spectroscopy, or proton nuclear magnetic resonance, and infrared spectroscopy have made identification and structural determination of compounds a routine. Models are developed to explain certain phenomena that may not be observable. For example, spectra are based on bond vibration model. Okay, empirical and molecular formula review. Example 1. The chemical composition by percentage mass of an unknown organic compound was found to be 62.02% carbon, 10.44% hydrogen, and the rest is oxygen. We're going to calculate the empirical formula of the compound. First, assume 100 grams of the sample. Assume we have 100 grams of the sample and find the amount in moles of each element. So, use a bit of the math that we learned from a stoic. We've got 62 grams of carbon because we know we had 62% and we know we've got 100 grams of the sample. We're going to convert this to moles using molar mass conversion factor to get 5.164. Then do the same for hydrogen and oxygen. You then have molar ratios. Don't round them up. Next, we're going to divide by the lowest value to find the lowest ratio. So you've got moles of carbon divided by the lowest one was the moles of oxygen, gives us 3. Do the same for hydrogen and do the same for oxygen, which is actually going to be 1. And you can see you've got a ratio of 3, 6, 1. So the empirical formula will be C3H6O. Next, the relative molecular mass of the compound was found by mass spectroscopy to be 116. We can deduce the molecular formula of the compound. And C, we're going to identify the possible classes of the compound. So to find the ratio of the actual molecular mass and the molecular mass of the empirical formula, you look at the ratio of the molecular mass of the actual compound. You can divide it by the empirical formula. We're given the molecular mass because we've used mass spectroscopy. It's 116. We know the empirical formula because we've just calculated it. Add them together, it was 58. When you divide it by 2 and divide it, you get 2. And so we know that the molecular formula is twice the empirical formula. The empirical formula is C3H6O. Molecular formula will be C6H12O2. And so we've got 2 oxygens. So we can kind of guess that it's going to be a carboxylic acid or an ester. Mass spectroscopy can be used to determine the abundance of isotopes in an element. For example, this is a mass spectrum of boron here. You can see we've got 2 peaks. One peak with a mass charge ratio of 10, one peak with a mass charge ratio of 11. We've got roughly 80%, 10, and around about 20%, 11. And boron has 2 isotopes, boron 10, this one here, and boron 11. So they've got slightly different mass. And there's obviously more natural abundance, there's more boron 10. The mass spectrum data can be used to find the relative atomic mass of an element. Structure of molecules. The mass spectrum for methanol is shown below, and it's simplified a little bit, but methanol is fragmented into different cations. The mass charge values for the cations help in the determination of the structure of the molecule. We'll get into some detail about that. The mass spectra gives information about the fragments formed when an organic molecule breaks into smaller pieces. Different sized fragments have different masses. So the peaks are just fragments of the molecule. Okay, so each peak here is just a fragment of the broken up molecule. Mz is mass to charge ratio. However, most fragments just have a charge of +1. So the Mz value is really just the mass of the fragment. This is a mass spectrum of methane, and the first peak at 16 is a methane molecule with one electron knocked off. Next, you'd have a CH3, so you've lost one proton. 14, you've lost 2 protons. 13, you've lost 3 protons. And 12, you just have a carbon. A sample M is introduced into the mass spectrometer and bombarded with high-speed electrons. These high-speed electrons knock out an electron from the molecule. So you have your substance and you smash it with loads of electrons. The electrons remove electrons that belong to the substance. So you end up with a cation. This first step produces the molecular ion, M+. So it's just what you started with minus an electron. Here you will have the mass spectrum for ethanol. You can see the first peak is at 46, which is what you'd expect. The peak with the highest MZ value is most likely just the molecular ion, M+. Since the charge is 1+, the mass to charge ratio value for the molecular ion is the relative molecular mass of the compound. Okay, so we'll go back up here. If this was ethanol, you're just losing an electron. You're just knocking one electron off. So this is going to have the same mass as this. So ethanol plus the ion has the same mass as the ethanol molecule. And it's 46. So you've got M plus is C2H5OH plus it's lost one electron. Then fragments are formed, other fragments. The molecular ion M plus will break down in the mass spectrometer to produce smaller fragments. One fragment is charged and the other is uncharged. So you've got this fragment, M plus, say, imagine it was the ethanol from the previous slide. It gets broken into 2 smaller fragments. One has a positive charge, one doesn't have a charge. Only charged fragments with a positive charge, only cations, will be detected and will show as peaks on the mass spectrum. The uncharged fragments will not be detected. Let's deduce the formula and mass of the molecular ion and fragments of ethanol. So the first, the ethanol itself with 1 electron removed is going to have a molecular mass of 46. Over here you see we've chopped off the oxygen and the hydrogen. We've got rid of the OH group to give us CH3, CH2 plus, molar mass of 29. Another possible fragment is just the methyl group here, positive charge. You could have the CH2OH plus, that's going to have a molecular mass of 31. And here you've got CH3, CH2 and oxygen. You just lost 1 proton, haven't you? And that would have a molecular mass 1 less than the original of 45. Okay, let's look at an example. Let's identify the fragments responsible for each peak in the mass spectrum for ethanol. Well, we know that the top one with a molecular mass of 46 is just the ethanol itself, which has lost 1 electron. Next, we've got a mass charge ratio of 45, 1 less, so it's lost a proton, so it's C2H5O+. Over here, we've got the CH2OH fragment, it's lost the methyl group. Next, C2H5, we've got the C2H5 here, we've lost the hydroxyl group. And finally, we've got this peak down here of 15, which is just the methyl group at the end. Fragmentations produce 1 cation and 1 uncharged particle, as we know. The fragment that gives the most stable ion forms. Only the charged species is detected. In the first example here, we've got 2 possibilities for splitting between the carbon-carbon bond in ethanol. Here would have peak 15 for CH3+. You see this is the charged one, and then we get no peak for this, it isn't charged. But it could go the other way, and you could get a peak at 31 for this, but this one wouldn't be charged, so you'd get no peak here. So you'd probably get a peak at 15 and at 31 because of both of these are acceptable splittings. In this example, we'll see splitting the carbon-oxygen bond in ethanol molecular ion. We're going to get a peak at 29 here. We'll get the positive C2H5 formed, but we're not going to get a peak at 17. OH plus doesn't form. This would be highly unstable. Hydroxyl group like to be negative. Analyzing mass spectra. So first, step 1, we find the molecular ion M+, and find the relative molecular mass. Next, we find the molecular formula of the substance using empirical formula data given in the question. Then we look at mass differences of the fragments to determine what is lost from the molecular ion. Then deduce the formula of fragments on the spectrum. So if we look here, you can see if we've lost 15, it's going to be CH3. If we've lost 17, OH. If we've lost 29, C2H5 or CHO. If we've lost 31, CH3O. If we've lost 45, we've lost COOH. Okay? And so it's worth knowing these numbers. These are the very typical fragments. You can see date table 28 in the data booklet too. Then you determine the structural formula. Let's do some examples. Example 1. The mass spectrum for pentane shown below. State the formula for each fragment. 72 is obviously just the pentane having lost an electron. 57, we've lost 72 minus 57 is 15. We've lost 15, so we've lost the CH3. That's going to leave us with C4H9+. Next, 72 minus 43 is a loss of 29. That's a loss of C2H5, which gives us the C3H7. And finally, a loss of 43, which is not on our list. We do know if you just take it away, it gives us a C2H5 plus cation. Oops. Do take note that when identifying the fragments present on a mass spectrum, you always show the positive charge. Lost fragments don't have a charge and so aren't detected on the MS. So be clear. Write your charges and don't write your charges if you're showing how you got an answer. Example 2. These two mass spectra are for two isomers, C3H6O. We're going to deduce their structures. Spectrum A and spectrum B. A and B have the same molecular formula, so have the same molecular ion, M+. And you can see it has a molecular mass of 58. And this matches the general molecular formula for an aldehyde or ketone, CnH2nO. Okay, so this matches either aldehyde or ketone. So which is it going to be? Well, spectrum A, we'll do some fragment analysis. First one is 57. It's got a mass difference of 1, and so you can probably guess we've lost a proton. So the C3H5O plus present. Next, a loss of 29. So we may have lost C2H5, which would leave us with CHO plus, or we could have lost a CHO, which would leave us with C2H5 plus. And finally, loss of 29. This is a mass difference of 1 from the 29 from this one, so it's probably just a proton loss from the 29 fragment. Therefore, the structure is as follows. We've got the C3H5O, which would be this section here, just having lost a proton. We could have a C2H5, there we go there, or we could have a CHO, this fragment here. So we can be fairly certain that this is what it is. Spectrum B, first mass difference is we're losing, if the peaks are 43, so we're losing 15, so we're losing the CH3, which would leave us with a C2H3O, and then we are losing 15, which would leave us with 43, and so we're losing the C2H3O. It's not on the table, but it's fairly easy to work out. And this would leave us with a CH3+. So it's fairly simple. and so the structure will be the ketone. We've got C2HCO here, just losing one methyl group, or obviously the other way around, lose this whole group, be left with a methyl. That's an intentional black page. You can do with it as you will. Example 3. A substance with the empirical formula CH2O has a simplified mass spectrum. Deduce the molecular formula and the structure. Well, the molecular peak M+ is at 60. And so the ratio of relative molecular masses here would be the actual is 60, and we can add it up. We know it's CH2O, so we've got a 12 for the carbon, 2 for the hydrogen, 16 for the oxygen. Do the math, you can see it's twice, so the actual molecular mass is twice the empirical formula. So the molecular formula will be twice this, so we'll have C2H4O2. We know this kind of thing here, when you've got no O2, probably carboxylic acids or esters. Continue. So we know C2H4O2 plus is 60. Let's do our fragment analysis. The first peaks are 45, so we've lost to 15. We're losing CH3, which means CHO2 plus is present. You could also write it like this. Next peak is a 43, so we've lost 17. Will be an OH group. C2H3O is present. Again, we could write it differently like this. And here, the peak at 15. We lost one which is 45, which is the COOH group. The CH3 plus is present. So the structure is as follows, and that's fairly obvious because we've got carboxylic acid group here, there, or the CH3CO, which is CH3CO, will be this section here, or of course OH loss could be here, or the entire COOH loss here, leaving us with the methyl group. The structure must be a carboxylic acid because an OH group was lost from the structure. Esters don't have OH groups, so you know it's not the ester. Example 4, a challenge. The mass spectrum for compound X is as follows. Okay, press pause and see if you can guess which one it is. Well, it can't be this one because the molecular mass doesn't equal 86. This one here should have peaks at 15, 43 and 71. It doesn't on here, so it can't be this. And you can't form fragments 29 or 57 with this setup, so it must be D. Splendid.